Welcome. In this video series, we're going to talk about algorithms and complexity. So typically when we write code, especially when we're writing bigger programs, we want to know how efficient our code is. So we're going to need to do some operation counting, meaning we're going to have to count the number of operations that code will accumulate in the worst case scenario. So that's really key here. There are other types of analysis. There's the best case analysis, the average runtime analysis. We're only going to consider the worst case analysis here. So to keep things really simple, we're going to only assume that the following count as floating point operations. In fact, each one of these things will count as one floating point operation. We're just going to call this flops for floating point operations. So anytime we're going to make an assignment to a variable, anytime we do any arithmetic, addition, subtraction, multiplication, division, we're really going to limit ourselves to these things. So anytime you see an assignment to a variable, that's going to count as one operation or one flop. Anytime something is added, it will count as one flop. So let's take a look at this line of code and see if we can conduct this analysis. In this particular analysis, we have a function called sample function. It has one input variable called n. And then when you call this function, an assignment is made. So k equals 2. That's going to require one floating point operation. So right there, we'll have one flop. And now we're not going to worry about comparisons. Typically, when you do a more rigorous analysis, you do account for the fact that this comparison has to take place, and it does take some time to do that. Now again, we're doing the worst case analysis. So that means if this is not going to count as a flop, we have to ask ourselves, well, suppose that if that condition is satisfied, suppose that n is in fact bigger than our k value, that what the user inputs is in fact bigger than our k, then something's going to happen. And that's going to require some time for that thing to happen. Here we have an addition and we have an assignment. So that's going to count as two total flops, once for the addition and once for the assignment. So our running total, our total so far, is going to, our total flops is going to be the sum of all the individual flops that have to be executed. So we have one, and then we're going to have plus the two more that we have down here. The next piece of our code draws us into a for loop. So a for loop will execute however many times our indices state. So this says from 0 to 10. So the index I will start at 0, and then this action will be performed. N will be reassigned a value, and that value will be the difference between the current value of n and the current value of k. So what's going to happen when we enter this loop is this is going to require 2 flops per iteration. By iteration, we just mean the individual runs. So the question is, how many times is this going to happen? Well, first of all, I is going to equal 0, and that's going to give us 2 flops. And when then once those 2 flops happen, I will increase to 1, and then we'll have 2 more. Then I becomes 2, so it circles back around, right? We're going to kind of loop over this 2 flop iteration, and we're going to do that until we reach I equals 10. So how many times did this have to run? Well, it had to run, we have to count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's going to be a total of 11 iterations. Okay, so in this particular case, this code will run, in the worst case, it'll run 2 flops per iteration. So this will be 2, if we do the unidimensional analysis, this is 2 flops per iteration. And then how many iterations are we going to have? Well, we're going to have 11 of them, 11 iterations. And when we multiply those two quantities together, we will end up with units of flops. So this is going to require 22 flops in total. And so we had to have 1 flop here, 2 more flops here, 22 flops here. So when we add those together, our worst case runtime is going to be 25 flops. Now that's the worst case scenario. The best case scenario is, of course, this is going to happen no matter what when you call this function. Same with these 22 flops down here. The only thing that could vary is that if n is not greater than k, then we get to save 2 flops and the runtime would be 23 flops instead of the 25 that we ended up with here. In this next example, we want to do the same thing. How many flops will the following pseudocode require? So our function here is called sample function 2. Again, it has an input of n. The first thing that we're going to do is we're going to make an assignment. So that's going to require 1 flop. And now we're going to have a nested loop. So in this nested loop, we have to think about how many times this is going to run. Well, I'm going to go inside of the body of the innermost loop because this is an easy count. This is going to require 2 flops, but that's going to be per iteration, per 1 iteration. Every time this function runs, 2 flops are going to take place. The next thing we need to determine is how many iterations will there be. Well, this innermost one, we kind of back our way out, we work our way out. This is going to run from 0 to 2n. So that means it's going to have, it's going to start at 0, we're going to include 0, and then we're going to go 2n more times. So this is going to run for 2n plus 1 iterations. Why is it 2n plus 1? Because it starts at 0, and we're starting at 0, we're counting 0, but then we're going 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 2n plus 1. Now this will run 2n plus 1 times, but then those 2n plus 1 iterations will be performed n times. So n iterations. And so an easier way to think about this is, suppose, like, for example, let's say we assign n to be 1 to keep this really simple. So the first thing that's going to happen is I is going to be assigned 0. J is going to be assigned 0, and then there's going to be 2 flops. So we'll keep track of the total number of flops here. Now the next thing that happens is I stays 0 because we're going to go down this way. This is going to run now, and so that means J is going to increase from 0 to 1. So I will equal, now in this case, 0, J is increased to 1, and 2 flops will take place. Now, so since n is 1, 2n will be 2 times 1, which is 2, so we still have 1 more index value to go. I will be 0, j will be 2, and 2 flops will take place. Now that we're out of j values, we've reached j equals 2 since n equals 1. Now we're going to go back up here. We're going to increase the counter from I equals 0 to I equals 1. And so this is our last index value for I, because I goes from 0 to 1. So now j resets, and j becomes 0. And so now we're going to do 2 flops. I remains 1. Now this is going to back up, increase the value of j. J becomes 1. And this is going to require 2 flops. I remains 1 while j increases to 2, and it will have 2 more flops, and that's 2 plus 2 plus 2 plus 2 plus 2. That's 6 times 2, which is going to require 12 flops. Now, if you notice that really what happened here is this thing here ran, and we said n iterations is actually n plus 1 because we're including 0 once again, so this should be n plus 1 iterations. So notice what we really did is this ran twice. The inner loop ran 3 times. 2 times 3 is 6. That means there'll be 6 total iterations of 2 flops. 6 times 2 is 12. So what really happened is, if you think about it, this is kind of iterations per iteration. I'm sorry, other way around. This one here, in the inner one, is how many times this will iterate 2n plus 1 per iteration of outer loop. And this is n plus 1 iterations of the outer loop. Okay, so this is going to iterate by itself, but it's going to be repeated n plus 1 times. So if we do the math on this, we can see that it's going to require 1 flop up here, plus it's going to require the 2 flops. I'm going to put this over here, but we need to count how many times those 2 flops are going to take place. Well, on the innermost level, they're going to take place 2n plus 1 times, and then those things are going to occur n plus 1 times in total. So really what it boiled down to is multiplying these two values together. That's going to give us the total number of times we're going to perform 2 flops. So if you do the dimensional analysis on this, this is iterations of outer loop, iterations of outer loop. This is going to be iterations per iteration of outer loop. And this is going to be flops per iteration. And so now these units cancel, and you can see that we're counting the total number of flops. So our final answer is can be written like this: 1 plus quantity n plus 1 times 2n plus 1 times 2. Now, if we do a little bit of expansion on this, and we're going to see why we're going to want to do this, if I do some foiling here on this, I'll get 2n squared. I'll have a plus n plus a 2n, which is plus 3n, plus 1. And that's multiplied by 2, and then plus my 1 over here. And if I reduce that even further, I'll have 4n squared plus 6n. Here I'll have a plus 2 plus a 1. So that is the simplest form that I could write that loop in. Now, the fact that it's quadratic is going to be important because that's going to help us define the time complexity of that function. So the time complexity function is a function whose output is the total number of flops required as a function of any input variables that affect the total number of flops. So you notice that here our time complexity function would really just be a constant 25. Again, worst case. So we would write, for example, 1. We would have written our time complexity function. Usually use the t of notation. For example 1, we would have said that t of n is equal to 25, or you could have just said t is equal to 25. The number of times this loop ran did not really depend on the value of n in the worst case. In example 2, we just found our time complexity function to be t of n equals 4n squared plus 6n plus 3. And here you could see that the input, the value that affected the number of times this would run would be the value that the user passed to that function. Of course, we assumed that it was in a non-negative integer value and all that stuff, but this would be our time complexity function. So the output of this should be the number of flops. The input is the number of times the size of n. So as our checkup here, we noticed that this would have required, this particular example, when n was equal to 1, we would have had 1 flop here plus the 12 more flops. That's 13 flops. Let's just double check that our function tells us the same thing. T of 1 would be 4 times 1 squared plus 6 times 1 plus 3, which is 4 plus 6 is 10 plus 3 is 13, and that matches exactly what we got up here. Here we just now have it symbolically so that we could count the number of total operations for any value of n. Now the one interesting thing to note is that if you were to graph these functions and you were to take a look at them as the value of t versus the value of n, here no matter how big of a value the user inputs, and I'm going to kind of skip some lines here, but the runtime of this function is a constant 25 operations. Again, we're assuming worst case here for both instances. But here what happens is I have to run more and more flops, or I have to perform more and more flops as the size of n increases. So in this case, we're going to have a quadratic function that we know that starts to grow more and more rapidly. So this particular code will become less and less efficient as n gets extremely large. You can see this thing will just continue to blow up at a quadratic rate. In the next video, we'll start to think about order of these guys.